Alright, now let's take a step back and look at the high-level design principles in the design of data structures. Alright, so when designing a new data structure, we need to spell out two things: the specification as well as the implementation. Right, the specification is like a contract, so it tells the users of a data structure what it does, and it allows other people to use it. Right, and implementation is like under the hood, actually implements the data structure, and users typically should not need to know this, and this gives you a choice in terms of how you want to implement your data structure. Now, for the game of name that we just saw, the following is how we would look at this problem. Now, so for the specification, right, what it does, we have the coins, and essentially you have to know how many piles there are and how many in each pile, right? Now, the other thing you have is that you have functions that let you interact with the game state. So there's a size and another function to remove coins from the piles, right? Now, we showed two ways of implementing the data structure. One is use an integer, right? The other one is use a tuple. Now, specification describes the data structure, so it gives an overview, right? And must state the assumptions, the contracts, basically the different aspects, okay, that the data structure must actually comply with, and some guarantees. And typically, you also give some examples in the specification. Okay, there are 4 different types of operations, as you know. These are the 4 types, okay? Let's look at an example. Now, suppose now we want to implement the list as a data structure, right? So a list is, let's take a look at how we will map up the specifications. So a list, right, is a collection of objects in a given order. So order is important. So for example, you can say that this is a list, right? So this empty list, and this is a list of 3 objects, 3, 4, and 1. You have constructors for the list, right? So these are the constructors. There's a list function. There's this also this empty list constructor. Selectors are what? Essentially, you have this operation. You can do slicing, you can do indexing. Predicates, right? You can have the type, check whether the object is a type list and whether something is inside a list. Printer, you just print, right? Now, another example specifications. Now, so a set, right, is an unordered collection of objects. Right, so this is different from a list because the list is ordered, right, and it does not have duplicates. Now a list can have duplicates, right? So for example, 3, 1, 2, and 1, 2, 3 are both sets. That is the same set, right? Empty set is the empty set, right? And 3, 3, 1, 2 is not a valid set. Okay, so we have the following constructors. You can make a set. You can adjoin a set, which means you add something to a set. You can union of 2 sets. You can join 2 sets together, okay, and you have also the intersection of 2 sets. So these are ways that you can construct a set. All right, selectors, you can't really select stuff from a set, right? So essentially, you have 2 predicates. Basically, one is whether something is element of a set, and the other one is that whether the set's empty, and you can print the set, right? So these are the specifications that you can have for a set object. All right, and a contract. Okay, what can a set do? So for example, a contract is that for any sets S and T, okay, an object X is element of X, right? For adjoint set XS must be true. So basically, what happens here is this adjoint set adds element X to S, right? So after that, this is a new set, and obviously it must contain X. So basically, the X must be an element of this new set, right? Now, its element of set X union ST is equal to its element of set XS or its element of set XT. So what does it mean? Basically, a union set, right, is a new set consisting of all elements of S and T. So if X is an element of S or X is an element of T, then X must be an element of the union. That's all. Okay, so this is a very simple thing that I'm just saying in more mathematical terms. Now, next thing is that its element of set X empty set is always false, right? Basically, empty set basically has nothing inside, so you definitely be false. So this, what we've shown you here, is an example of how you would set out the specification consisting of some definitions and the contracts. The contracts are some conditions that the data structure must meet. Okay, now that we have done the specifications, now we'll look at implementation. So in implementation, essentially we will pick a representation, right, and there are many choices, so we pick something. And then after that, different choices will affect your time and space complexity. And sometimes there will be some constraints that we will be imposing on the implementation, right? So for example, in the earlier case, we saw that in rational package, the denominator must not be 0. Okay, and then after that, we implement the different types of functions, constructors, selectors, predicates, and printers, right? And then you make sure that you satisfy all the contracts. okay, that we stated in the specifications. We'll move on to implement sets. Now let's take a look at the first possible implementation of sets, and we call it the unordered list representation. So the empty set is represented by empty list. That's fair enough, right? Each set is represented by a list of objects. Okay, and the main thing to do is to make sure we take care to avoid duplicates. Right, constructor basically makes set is nothing. Right, return empty set just returns the empty list. Predicates, okay, is empty set, and okay, you just check whether S is empty or not. If it's empty, then it's good, it's true. If it's not, it's not. Predicates, okay, is element of X S. Okay, so you check whether X is element of S. Okay, what do? Well, essentially, you just check if it's empty. Empty obviously is false, right? Otherwise, you just, for E in S, means every element E in S, you just check if E equal X, return true. If everything's gone, you finish and return false. Alright, kind of complexity of this operation will be order n, right? Where n is the size of the set. Constructor, okay, adjoining set. So you can add X to S. How does it do? Basically, if the X is not an element of S, then you just basically append X to S, right? Otherwise, you just return S. Time complexity of this is order n. Why? Because in the worst case, you check through every element of S to make sure that it is not inside, right? So next one, constructor intersection. Okay, this one I leave it to you to do exercise. You can do this and you post it in your answer in the forum, right? Just for kicks. All right, now let's look at an alternative implementation for sets. Now this is called the ordered list implementation. Essentially, we still use a list to represent a set, but now we store the objects in some way that is sorted. Okay. Now, first question is why would you want to do this now? The previous representation using the just non-ordered list seems to work, but why do we bother? Let's take a look. The interesting thing that we want to highlight here is that in this case, the specification does not specify that we have this constraint on the implementation. It means we did not specify that the object was stored in an ordered way, but we have decided ourselves to impose the additional constraint, right? But we also know that this is a little bit of an odd constraint in the sense that this is only possible like if the objects are somewhat comparable to each other. That means there's some natural ordering between objects. What do you mean? Numbers are obviously ordered, right? So 2 is bigger than 1, 3 is bigger than 2, and so forth. Strings are also ordered because there's a natural, what you call the lexicographical or dictionary ordering, right? Colors in general, not ordered. Now, let's take a look at implementation. For the constructions predicates, everything's the same. Okay, same, no difference. Whoops. Yeah. All right. Now, let's look at something else. Is element of X. Okay, how does it work now? Well, basically same thing. If it's empty, then it's return false. If not, then you check every element in S. Okay, if it's the same, return true. Now, the first thing you realize is that if E is bigger than S, you can already give up, right? Because the list is ordered. So you know you're going from smallest to biggest. Once the elements are bigger than your search element, you know it's done, right? So this is a bit different. Time complexity here is actually still order n, but it's slightly faster on average. Now, the interesting thing is other functions. Let's take a look at this example, intersection, which in the previous example, you're supposed to do for homework, right? If you did for homework, you realize that it's a little bit nasty, right? Because you have this 2 while loops that you need to loop through both sides. Now, in this case, let's say you have ordered sets. Then how would you do intersection? Well, you take 2 sets, you look at the head, right? Okay, if the same, it means 1 are the same for both sides. You know, yeah, there's 1 intersection. So 1 and 1 is in the intersection. Right, now next thing, 3 and 4, so they're not the same. So 3 is smaller than 4. So what you do is that we just remove 3, right? So now we have 4 and 4. Oh, you know, great. 4 and 4, intersection again, right? And we remove both. Now if 8 and 5, okay, we know that this is no good. So remove 5, okay. And then we have 6 and 8, you remove 6 because, you know, no good. 8, 8, great. No, we have this, right? And now set 1 is empty, so you cannot intersect with set 2. Okay, so we're done. In other words, we have 3 elements, which is 1, 4, and 8, which are in the intersection of these 2 sets. Okay, let's take a look at the code. Intersection set 1 and 2. Okay, now if the 2 sets are empty, then it's empty, right? So this is cool, right? Now, then you create a result, which is empty list, and then we have 2 indices 0, 0. And then we have while loop, right? And we are inside the while loop as long as the indices for I and j are within S1 and S2 respectively. If the first elements of both sets are the same, then we know, okay, this is in the intersection. we'll add that element into this result, okay, and then we will advance the index for both sets. If the left one is less than the right one, we just increment that one, okay. Otherwise, we know that the right one is bigger, so increment that one, right? And then at the end, we just return result when everything is done, all right? So complexity of this thing is actually order n, right? But it's faster than the previous version, okay? Because the previous version, if you use the unordered set, you need to do this nested for loops. So you're likely to have to do n squared, right? Now, the next thing we can do is we can have another representation, which is a binary tree. And essentially, a binary tree is the following. You have empty set represented by empty tree. Basically, the elements are also sorted. So what is a binary tree? Okay, so in a binary tree, each node stores one object. Okay, and the left subtree contains all the objects that are smaller than this one object. And the right subtree contains objects that are greater than this object. This is a binary tree. So here is 7. Everything else on the left is smaller. Okay, everything on the right is bigger. This is also a binary tree, right? Everything on the left is smaller, everything else on the right is bigger, and this is also a binary tree. Okay, so essentially these 3 trees will represent the same set, 1, 3, 5, 7, 9, 11. Right, and these are the operations to make a tree. You make tree, the basic element in the current node, the left subtree, and the right subtree. Okay, to get n trees, return the first thing, left branch is the second thing, and the right branch is the third thing. It's element x in the set S. If S is empty, obviously not, right? If X is the current entry, answer is yes. If not, then you check. If X is less than the current entry, you go to the left tree. If not, you go to the right tree. So you check. Now you recurse down to the left side, you take the left branch, and you check whether it's element of X in the left branch. Otherwise, you try the right branch. Okay. Time complexity of this thing will actually be, well, order log n. Okay. Similarly, if you do a join set, right, then you have to add a new element. Okay, we check whether it is empty, then you just create a new tree, and it's the x is already the element means it's already inside, so you just return s. All right. So essentially, if your x, the new element, right, is smaller than this one, you basically create a new entry, right, and then you adjoin the left branch on the left side, and then you keep the right branch. Similarly, you do the converse for when x is bigger than n3. Okay, now we just said that this order of growth is log n, but the assumption is that the tree is balanced. Okay, if the tree is like this is actually a valid tree. Okay, but obviously this is nasty because this one will be order n, right? It's not order log n, it's order n for all operations because it's actually to go down the entire tree, which is the whole length. So this is called an unbalanced tree. Right, and basically it will break the log n complexity. So one thing you need to do is to rebalance the tree, and you need to create a new function that will actually restore the balance, and we call it every now and then. Right, so how would you convert an unbalanced tree into a balanced tree? So for homework, you can write the function balance tree that will take the binary tree and return the balanced version. Okay. So we have seen the examples that for compound data, you have many potential representations that you can choose. Okay, sets you can choose as unordered list without duplicates, ordered list without duplicates, or you can have it as a binary tree. Okay, again without duplicates. Right. The main thing is that each representation has its own pros and cons. Right. Typically, some operations are more efficient, others less efficient. The best representation depends on how the object is being used.